All right, I think it's time to get started. Welcome back. Nice to be here with you all on a Tuesday. Folks back home, wish you were here. Let's talk some more about trigonometric integrals. That's what this section is about. By the way, we got homework due tomorrow. Hope you've had a chance to check it out. It's maybe a little longer than usual because we had some extra stuff from the previous week. Hope it's not too long. Last time we were talking about doing integrals like this, and I just want to refresh your memory. These can be a little long-winded, and I don't think we have to go through the whole thing, but the section trigonometric integrals is about how do you do the integral of some power of sine times some power of cosine. And the trick that we had before is when one of the powers is odd, which is the case in this, one or both, it's fine if both of them are odd, but when one power is odd, you save one of them. This is like the slogan, save one, and then write the rest, which will be even. So in this case, I'm looking at the sine here. There's three, the power on the sine is odd. So I'm going to save one of them, and there will be two left over. And then you write the rest of them, that is the two left over ones, in terms of the other function, using this sine squared plus cosine squared equals 1. So in this example, what that looks like is I'm going to pull out one of the sines, leaving sine squared. Of course, I also have cosine to the 4. And then I'm going to put the other, the one that I'm saving over here. That's because eventually I'm going to do a U substitution where the sine x goes with the dx. So this is what is meant by save one of them, and then write the rest of them in terms of the other function using sine squared plus cosine squared equals 1. So in this case, I'm going to use the remaining sine squared, I'm going to replace by 1 minus cosine squared. All right. These screens look blurry to me today. Do they always look like that? Yeah, all right. I didn't notice. I hope you can still read it. Okay, so now everything is written in terms of cosines, except for that one extra sign at the end, but actually that extra sign at the end is going to help us out to do the U substitution. So now I'm going to do the substitution, U equals cosine x, and the du equals sine x dx. This is why I saved one of the signs, because it means I can turn this where I see sine x dx, that becomes du. And then the rest of it is just the polynomial, 1 minus u squared times u to the 4. And this now becomes an integral you can do. Right? You have to rearrange it a little bit because I have slightly complicated polynomial in there, but you would just distribute that u to the 4. So it becomes u to the 4 minus u to the 6 du. And we do the integral. I said we didn't have to do the whole thing. We might as well. I mean, it's easy from this point. You get 1/5 u to the 5 minus 1/7 u to the 7 plus c. And then I plug the original variables back in. So 1/5 cosine to the 5x minus 1/7 cosine to the 7x. And this is the save one of them trick. All right? We did several examples like this last time. Anybody got any questions about this?
Yeah, how did you go from, like if you scroll up a little bit?
Yeah.
Sine squared x cosine to the 4th x down to the second one.
Yeah, so we use this thing here. If you subtract cosine squared from the right, just rearrange that. It'll say sine squared x equals 1 minus cosine squared x.
Okay.
Yeah.
Professor, theoretically, because these two are products, could you do integration by parts on that?
You could. You mean
From the original.
from the very beginning?
Third goes to the 4th. Could you use sine as your u and cos as your dv in that
This is not a bad idea, although I think it will work, although what I just did is probably easier, but we can still think about that. This, I would say, you have to choose. The problem is when you're doing integration by parts, the u and the dv have to multiply up to be the entire thing inside the integral. So if you want to choose them, you have to do something like this. Which is, it's going to get complicated, because then du becomes 3 sine squared x cosine x, and v is kind of impossible to do. V is the integral of cos to the 4x, and this, there isn't a very good way. I mean, maybe there is a formula, but it will be very complicated. And so after you do the parts, you're going to end up with another integral which is more complicated than what you started with. So not a bad idea, but yeah. I mean, you could try to do something weirder than that. You could pick the u to be just one of the sines, and then the dv to be sine squared x cosine to the 4x, but that also, you're going to have a hard time integrating. So, yeah. Great. Okay, so this was the method that we talked about last time, and this will allow you to handle when one or the other or both of the powers are odd, right? Then you can save one of them. The remaining thing will be even, and so you can write it in terms of the other trig function. What remains is to talk about the situation when both powers are even. So what about when both powers are even? And for that case, we use a completely different trick. And it's based on some formulas that I wrote last time that I will refresh your memory about. We use these weird formulas. Sine squared of x equals 1/2 1 minus cosine 2x. Cosine squared of x equals 1/2 1 plus cosine 2x. Now, these I won't expect you to memorize. If I want you to do this, like on our next test, for example, I will just give you a big list of random formulas for you to use. And I want to say, looking back at my notes, and I watched the video again last time because I realized that I wrote one of these formulas wrong. So if you flip back a page, you may see this written incorrectly. Yesterday when I wrote this, I wrote it 2 times. Once I did it correctly, and the other time I did it wrong. I never actually used these formulas last time, but I think I wrote this one down incorrectly. I think I put a sign in there, but it should be cosine. It is 1 plus cosine of 2x. Yeah. Yeah, I think last time I wrote it as a sine, but it's not a sine. They're both cosines. Sorry about that. If I never, like I said, we never actually used these, so I didn't really do a problem wrong using the wrong formula, but I did write it incorrectly. Okay, and occasionally we will also use, here's another variation on these. Sine squared of 2x, you'll see why this becomes important in the examples. This is not exactly a new formula. I'm just going to write the first formula again, but plugging in 2x instead of x. What it says then would be 1/2 1 minus cosine of 4x. And similarly, cosine of 2x is 1/2 1 plus cosine of 4x. These are not really new formulas. They're just, I wrote the first 2 formulas again, but I used 2x in place of x. All right? But anyway, we are going to use these. And in some very complicated examples, you might want to use sine squared of 4x, which would be 1/2 1 minus cosine of 8x. Yeah, it would multiply these numbers by 2 every time you do it. But we're actually not going to do any that require that. All right. Let's just try a simple example when both powers are even. You have to do you have to kind of get a feel for these. So let's try integral of sine to the 4x dx. This has no cosines, just sines. It is an even number of them. All right. So sine to the 4x. You want to, first of all, think of this in terms of sine squareds. This is integral of sine squared x squared, right? And when all the powers are even, you will always be able to do that. You can rewrite whatever you started with in terms of powers of sine squared and powers of cosine squared. That's because this trick will work when all the powers are even, all right? If you have an odd power, there'll be some leftover thing, which is actually good. You should use the other strategy in that case. Anyway, what are we going to do with this? We're going to use that formula above for sine squared of x and plug it in right there. So it becomes integral 1/2 1 minus cosine 2x squared, right? Make sure you put everything inside the squaring like that. And now this, how can we do the squaring in there? We can just do like the FOIL thing. You got to expand this squaring. First of all, the 1/2 gets squared and becomes a 1/4. And I'm just going to write that outside the integral because we might as well. And then what remains is 1 minus cosine 2x squared, right? And that, I'm going to do, expand that like the FOIL thing. So this becomes integral of, at the beginning I get 1. So what I'm doing is 1 minus cosine 2x times 1 minus cosine 2x, right? So I get 1 at the beginning, then I get minus 2 cosine 2x. And at the end, plus cosine squared of 2x. All right. And as I look at this, I kind of like most of this, right? Like if I was actually going to do this integral, which I am, the integral of 1 is no problem. That becomes x. The integral of this, cosine of 2x, will become 1/2 sine of 2x. Remember this, I'm going to use this formula, integral of, well, in this case it's cosine. Integral of cosine kx is 1/k sine of kx. Remember that guy? So we can do cosine of 2x. There's no problem, right? That's an easy integral to do. Cosine squared of 2x I'm a little concerned about because we don't have a cute formula for the integral of cosine squared of x. But if you look just a bit up in your notes, you will see we do have a cute formula just for what cosine squared of 2x is. So I'm going to rewrite this cosine squared of 2x, rewrite it as that. And what are we going to have? So all this other stuff I'm satisfied with already because I can do those integrals no problem. Now I go plus cosine squared of 2x is slightly off the screen. There it is. 1/2 1 plus cosine of 4x. All right. And now pretty much everything here is something I know how to do the integral of, right? Using this guy here. Cosine of kx. So one is, here is a cosine of 2x, here's a cosine of 4x, but they're the same. Those are both easy to do. Before I do that, let's just simplify a little bit. The constant in front will just stay a constant in front when you do the antiderivative. Just as always, you know, like integral of 3x squared. The 3 stays like it is, and then you do whatever you do with the x squared, right? Yeah, so those constants in the front also do not cause any problem. Just to clean stuff up a little bit, can we distribute the 1/2 here? And then maybe something will simplify a little bit. This is not a big deal, but just to keep it all straight. So it's going to be 1 minus 2 cosine 2x. Distributing here, plus 1/2 plus 1/2 cosine 4x. And if you like, you can even combine these constants. I have a 1 here. I have a plus 1/2 here. Those can add up to be 3/2. Sometimes when you do this, some of the cosines might add together, but it didn't happen in this case. But let's do that then. Not a big deal, but we might as well. So 3/2 minus 2 cosine 2x plus 1/2 cosine 4x. And now we can just do the integrals down the line, all right? I got 1/4 in the front. What happens to 3/2? Take the integral, what do you get? Yeah, 3/2 x, right? Just a constant gives you that same constant times x. Okay, minus 2 cosine 2x becomes 2 times 1/2 sine 2x plus 1/2 cosine 4x becomes 1/2 times 1/4 sine 4x. I am using that thing about integral of cosine kx is 1 over k sine kx. And there's a similar one for the sine. All right? And that's the answer. What do you think? Any questions about that? I guess you could simplify those coefficients a little bit if you want to, but I don't care so much about that. It's a strange trick, but it's based on using these formulas here over and over again until you know, the purpose of these formulas, each time you use it, it reduces that exponent by 1. So if you do it enough times, eventually everything will just be something like cosine of 2x or cosine of 4x or whatever. That's the idea. All right, let's try another one, and then I got one for you all to try, because that's how I do it. Let's try integral sine squared x cosine squared x. So the powers are all even here, which means, so that's the first thing you should look at it and decide kind of what your strategy is going to be. The powers are all even, so your strategy is not save one and do a U substitution, but it's use these other double angle formulas or half angle formulas, whatever you want to call them. You should use those formulas to either change the sine squared into some kind of cosines or change the cosine squared into some kind of sines. And there are many ways that you could approach this one, but the way that I'm gonna do this is change everything into sines first. And the way I'm going to do that is using the same stuff that we did in the other method, which is to say I'm going to write sine squared x and then 1 minus sine squared x here. All right, cosine squared is 1 minus sine squared. So you can always turn cosines into sines in that way, provided that it's squareds, right? That's why it's important that the powers all be even in order for this to work. All right, and then I'm going to distribute here, and we will have sine squared x minus sine to the 4x, right? And now that everything is like this, we're going to use dem formulas from the very beginning. So this I'm going to write as my sine squared x, first of all, is going to be, sorry, I realized I have a typo in my paper. Doesn't matter. For the sine squared, I'm going to write 1/2 and then 1 minus cosine 2x, right? And then sine to the 4, I'm going to think of this, just like in the previous example, as sine squared x, the whole thing squared. So this is going to become minus 1/2, 1 minus cosine 2x squared, right? That's sine squared squared again. And this, we do the FOIL and then recombine everything, and it should work out like the previous example. Everybody good so far? This is sort of the first step is like that. All right, so what do we get here? Just kind of clean things up. Distribute the first 1/2 there. It's going to be 1/2 minus 1/2 cosine 2x. Both of those I like already, so those we're not going to have to work on anymore. The second part there, we got to square this out, right? And it'll look like the previous example. The 1/2 will square and become a 1/4. And then the rest of it, when we square it, we get 1 minus 2 cosine 2x plus cosine squared of 2x. And now these are all looking pretty good. Let's distribute the 1/4 and combine them, because we have some opportunity for combining these terms here.
Why is that? Oh, is that because you're squaring
Yeah, because the 1/2 gets squared in there, and then also that binomial part gets squared. So I got 1/2 minus 1/2 cosine 2x minus 1/4. I'm distributing the 1/4 here. Plus 1/2 cosine 2x minus 1/4 cosine squared 2x. And actually, I like this because you'll see this part cancels here and here. Minus 1/2 cosine x will cancel with plus 1/2 cosine x, which is nice. The constants can add together, but they don't fully cancel. We get 1/2 minus 1/4, which is 1/4. So I got a 1/4 here, minus 1/4. And then what am I going to do with cosine squared of 2x?
Turn it into the 1/2 1 plus cosine 4x.
Yeah, we got a formula for that, right? In that list of 4 formulas from the very beginning. This last one here. Cosine squared of 2x is 1/2 1 plus cosine 4x. So that goes right here. 1/2 1 plus cosine squared, not squared. That's the whole point of this, is it's not cosine squared anymore. It's just cosine, which is much easier to handle. Right, almost ready to actually do this integral. I got 1/4 here. Let's just distribute all of that business. So 1/4 and a 1/2 makes a 1/8. So it's going to be minus 1/8 and then minus 1/8 cosine 4x. Right? And now we can do the integral, or you could subtract if you want. 1/4 minus 1/8 is 1/8, I believe. So this is 1/8 minus 1/8 cosine 4x. And then we can just do these integrals. So I get 1/8 x minus 1/8 times 1/4 sine 4x. And that's that. It's as simple as that, right? This is just a lot of like individually kind of simple tricks, but it ends up being a kind of complicated process. Any thoughts about that? Any questions about that one? I got one for you all to try, but
I got a question.
Yes.
So I know, like when we changed the first thing from sine squared x, cosine squared x to sine squared x, like we changed the cosine to the sine. Like I know how we got it, but why do we?
this 1 minus sine squared? Yeah, so actually there are several ways that you could get this problem started, and this one, the way that I just did it is not the only way you could have done it. So you could also, if you don't want to turn them both into sines, it might occur to you that this, so here's a similar or a different strategy, I guess. You could just immediately use your formulas for sine squared x and cosine squared. This becomes 1/2 1 minus cosine 2x. And then times 1/2 1 plus cosine 2x, right? And then you could do the FOIL in there, and you would end up, you would end up basically at this step again after doing the FOIL in there. So if that seems easier, you could do it that way too. Etc. Yeah, good question. Any other thoughts? All right, I got one for you all to try then. So how about let's try the integral of cosine to the 4x. No sines in there, just cosine. See what you think. I'll give you a few minutes. And then we're going to move on to the next section after this. All right. Yes, that's great. You guys doing okay back home? I bet you are. Yeah.
Like separated the square. Yeah. Oh, yeah. Okay. Yeah.
Professor, I'm just saying honestly, for me, the class of trig, I really touched it.
Uh-huh. All right. Well, just got to keep straight which one's the derivative of which one. Oops. All right, let's talk about these. I was doing it up here myself. I hope that you, it looks like most people in the room at least are doing great. So cosine to the 4x, I would begin by writing this as cosine squared squared. Oh, see the chat. Yes, somebody just chatted that they're doing great. Thank you. I'm doing great too. Cosine to the 4, I write as cosine squared squared, and then the inner cosine squared, I use my formula about cosine squared of x is, you know, that half angle formula, this here. Still has a squared out here. I squared the 1/2 first and just took it out of the integral. You can leave it inside, but it messes things up in there. Then I have to do the FOIL on this, 1 plus cosine 2x. When I do the FOIL, I get this. These two, the first two terms look good to me, but I have to work on the cosine squared of 2x a little bit, and it becomes this. Some mathematicians refer to this as massaging the formula. That language makes me uncomfortable for some reason, but that's what we're doing here. We're just massaging the formula until it feels good, right? Okay, so this cosine squared 2x, that's that other formula, turns into that. And then rearranging, so I distributed the 1/2 and I get to here. I'm pretty much ready to do the integrals at this point. Maybe I'll add up the constants first. There's not really any cancellation inside, but I can add 1 plus 1/2 is 3/2. And then I got all this, the rest of this stuff here. And then we do the integrals. So 1/4 is on the outside, and then I get 3/2 x. That's the first part. 2 cosine 2x becomes, well, it's 2 times 1/2 sine of 2x. And then this one becomes 1/2 times 1/4 cosine 4x. Sine of 4x, sorry. Integral of cosine is sine. There you go. I hope you got that, or something like that.
Why is it 1/4 sine of 4x and 1/2 sine of 4x?
I'm using the old integral of cosine kx is 1 over k cosine kx. So that cosine of 4x becomes 1/4 sine of 4x. All right. These are a little tricky. You have to just remember the appropriate tricks to use. The individual steps are not hard, although there's plenty of opportunity to mess it up. Any thoughts about that? All right. Excellent. So this whole section was called Trigonometric Integrals. That is, doing integrals which have sines and cosines on the inside, products of sines and cosines. And by using these methods, in theory, you could do any integral of any product of sines times cosines. Now, if the powers are high, it would be sort of prohibitively many steps that you would have to do. But in theory, you could do it. If, for example, if this were cosine to the 6 instead of cosine to the 4, the difference would be, so if this were a 6, then I would make that a 3, and then I would make this a 3, and then instead of doing the FOIL with 2 things, I'd have to do it with 3 things, which is quite a bit more complicated, but you're going to end up with something, again, that looks more or less like this, only it's just going to have some more extra stuff in it, but you use the same techniques throughout. All right, so in theory, you could do any power of sine times any power of cosine using these tricks. All right, the next section has a similar sounding name, but it's actually a quite different batch of tricks, and in my opinion, this stuff that we just did is a little tricky. The next stuff is a little more tricky, I would say. I don't know if that's not good news, maybe. But the next section has a very similar name. It's called Trigonometric Substitution. All right, the one we just did is called Trigonometric Integrals. That is integrals which have sines and cosines on the inside. Trig Substitution, this is about when the integral itself doesn't have trig functions in it. So this trig substitution is used not for things which already have sines and cosines in them, but it's when the integral doesn't have trig functions inside. But we do a substitution which inserts trig functions where they didn't exist before. And this is what makes it a little harder, is you have to kind of cook up the trig functions out of nowhere. So when the integral doesn't have trig functions inside, but we introduce them using a substitution. All right. And I want to show you an example first where you might want to use trig substitution, and then we'll talk about how to do it. It involves a slightly weird kind of U substitution, which I want to talk about in the abstract first. But here's an example. This is useful for something like this, the integral from 0 to 1 of square root 1 minus x squared dx. How do you do this integral? The answer is you don't really, unless you know trig substitutions. But this integral here, I have, you might look at this and think maybe I'm going to do a U substitution just because you don't have any other way to handle this. You might choose 1 minus x squared as the u because it's inside the square root, but then you don't have the appropriate du. The du would be negative 2x dx, and there's not an extra x out there to make the substitution work. But this actually is often given as an example. You probably saw this example in your Calc 1 class. In fact, the answer of this is pi over 4. Why is that pi over 4? Does this look familiar to anybody? It's a very strange answer to get from a function which doesn't seem to have anything to do with trigonometry.
Oh, wait, is this substitution for sine, cosine, isn't it?
Yeah, it involves doing a weird substitution and creating sines and cosines on the inside of the integral where they didn't exist before. This is the basic idea behind trig substitution.
These are the definition of sine and cosine.
Maybe, I don't know. I wouldn't say it in those words. Let me just can I try and convince you that this integral actually does equal pi over 4? There's a simple trick for this. If you consider this as an area, geometrically, this is, of course, the area under the curve of y equals square root 1 minus x squared. But that is the same as writing, if I square both sides. This is the unit circle. So what I'm looking at here is the area under the curve where the curve is given by the unit circle. And the integral that I wrote is just from x equals 0 to 1. That would be this. Really, what I'm talking about is this area here, right? It's the area under the curve of the top half of the unit circle. It's the top half because of the square root sign. Gives me the positive values. This is 1/4 of the unit circle. And what is the area of a quarter of the unit circle? Where the entire unit circle, its area would be pi r squared, where r is 1. So the area of the whole circle is pi. And so that little piece of it has area pi over 4. So that's why the integral, its answer is pi over 4. Although this is a bit of an unsatisfying answer to me just because I still don't really understand how you would find the integral of that function in general. I just know that this answer happens to equal pi over 4. But for example, what if it was, instead of the integral 0 to 1, what if it was the integral 0 to a half? Then suddenly I have no idea what the answer is, because that would be some very weird looking portion of this. It would be only that much. And I have no idea what that area is. All right. Anyway, the trig substitution is meant to actually give you a good way to do integrals like this. That doesn't involve thinking of it in terms of an area of a circle. All right. But before we get to that, I want to just say a few notes about U substitution in general, because we're going to do some substitutions which are a little different from the standard way that I usually talk about U substitutions. So I'm going to talk about variations on U substitutions. They're not really variations per se, but just a few different ways of writing things, which when we do the examples in this section, it will be much more convenient to write it in a slightly different way than what I usually do. So variations on U substitutions. The typical thing would be something like the integral 0 to 3 e to the 2x dx. So this is a simple example, and first I'm just going to write this the way that I would usually do this using a U substitution, the way that I always write down when I do my U substitutions. I would say U is 2x. I choose the inside of the exponent to be my U. That means the du, what's the du going to be? 2 dx, right? And at this point I usually would divide by 2. to write 1/2 du equals dx. The reason I do this division is because I intend to plug in, instead of dx right here, I'm going to turn it into 1/2 du. So anyway, this becomes integral now e to the u times 1/2 du. I take the 1/2 out, it becomes integral of e to the u du, which of course is e to the u. And then I replace the x variable, so it's 1/2 e to the 2x. And now, remembering that this was a definite integral from 0 to 3, I'm going to plug in 0 and 3 for x. And I get 1/2 e to the 6 minus 1/2 e to the 0. E to the 0 is 1, of course, but I don't care about that so much. All right. Hopefully nothing here is strange. Like, this is the way we always do U substitutions. I would like to point out that the values here of 0 and 3, I didn't write them in the middle here. I reintroduced them at the end. The reason that I didn't write them here, it's technically not correct to put 0 and 3 there, because this now has become an integral with respect to u, and these values are not actually the values of u that you want to plug in. In fact, you don't want to plug in values for u. You want to plug in values for x. So it's not quite correct to put to continue writing the 0 and the 3. Now, there's another way to write down U substitution steps in this scenario, in which you actually do transform the x values into u values. And maybe you learned how to do this in high school or in your Calc 1 class. I usually don't do it that way, but there are some examples in this section when it is much more convenient to do it that way. So I just want to refresh our memory, or show you for the first time perhaps. Another way to do it. All right, another way is to translate those values into values of u. So I'm just going to do the same problem again. It's the same substitution. Du is 2 dx, and then I'm also still going to divide by that 1/2 here. But I'm also, at this point, going to transform the 0 and the 3, which are x values to begin with. Sorry, I forgot my dx. The 0 and the 3 refer to values of x. I'm going to translate them into the corresponding values of u. And so, for x equals 0, what is the value of u? Well, it would be 2 times 0, which is 0. And for x equals 3, what's the corresponding value of u? It would be 2 times 3. You're just plugging these numbers into the little formula for u here. This u value would be 6. All right, and then I can change this original integral into, now it becomes the integral 0 to 6 e to the u times 1/2 du. All right, I changed the values 0 to 6 because those are the appropriate values of u, which go along with the original values of x. Yeah.
Once you have that U substitution completed, like where it's even to u, do you even have to substitute that 2x back in, or do you just leave it?
That's right. So when we do it this way, at the end, we're not going to put the x values back in. We're going to just keep it as u's forever. Yeah. Anyway, can we just finish the problem and verify that we do get the same answer? So I'm going to pull the 1/2 out. 1/2 integral e to the u from 0 to 6. This becomes 1/2 e to the u when I do the antiderivative, and I plug in 0 and 6 for u. All right? I never go back to the x's here. I plug in the 6, I get 1/2 e to the 6. I plug in the 0, I get 1/2 e to the 0. And this is the same answer that we got before, all right? So this translation of the values, you have to do, and some people always do the U substitution this way, and that's fine. You have to do a little extra step up here, but it saves you the extra step at the end of putting the x's back in. So it's sort of an even trade. Any questions about that? So like I said, in the next section, it's going to be much more convenient to do it this way rather than the way that I usually do it. Okay? One more way. This is another way which is usually not a good idea to do it. So in this simple example here, this way which I'm about to show you is not really very helpful at all. But it is the basic approach to the trig substitutions that we're about to talk about. So yet another way is what the book calls inverse substitutions. This is going to look a little weird, but like I said, this is the basic approach to the trig substitutions, which we're about to do in the next section. The idea behind the inverse substitution is you look at the exponent here, it says 2x. The whole problem with this thing inside the integral is that 2, right? If there were no 2 there, then this would be an easy integral to do. So the idea behind the inverse substitution is you write x equals 1/2 u. The idea is I'm going to change the x so that it looks like 1/2 u. And then that 1/2, if I stick it in where the x is, will cancel that 2. And then everything will look great inside the integral. That's the idea here. Inverse substitution is because rather than the standard U substitution, I tell you what the U is in terms of x. But here I'm actually, you sort of start with the x and you say what the U is, what x is in terms of U. It's backwards somehow. But it still works just as well. Now in this particular example, there's no reason to do it this way. But like I said, in the examples we're about to do, this is the only way to do it. So if x is 1/2 du, if x is 1/2 u, you do the derivatives. Dx is 1/2 du, and you plug everything in over here. And I'm also going to translate the x values as before. Now this is a little strange. When x is 0, what's the corresponding u value? Well, you have to do a little bit more work here. You have to say 0 equals 1/2 u, and then solve this for u. U equals 0, right? And then when x is 3, I go 3 equals 1/2 of u, and I solve this for u. I get u equals 6. So this is a little more difficult, that step. Anyway, when I plug everything in, it becomes integral, this time 0 to 6, because those are the u values. And then e to the 2x becomes e to the 2 times 1/2 u. I plug x equals 1/2 u. And then dx equals 1/2 du. And then you simplify everything in the integral. I will pull the 1/2 out like we usually do. Integral 0 to 6, and then instead of e to the 2 times that 1/2 u, it's just e to the u, du. And now we are at the point of all those other problems, right? So I can just finish off. This is 1/2 e to the u, plugging in 0 and 6. Which is 1/2 e to the 6 minus 1/2 e to the 0. All right, that is what they call an inverse substitution. In this particular problem, there's no reason to do it this way. In the trig substitutions, you always have to do it this way. So I just want to make sure everyone is comfortable with this approach. It's a little weird, but it works just the same. Any questions about that? Inverse substitution. Okay. Let's see if we can go back and do that integral from before. It was this. Now, I know the answer is pi over 4. You get to pi over 4 by realizing that this is the area of a quarter circle. But I want to do it without that realization because that's not a very generally applicable method. That will only work for this very specific example. I want to do something that will work even if I change some of the features of this formula around a little bit. All right? Let's do it. Here's the idea. We do the substitution x equals sine theta. This is an inverse substitution because I'm telling you what the x is rather than telling you what the theta is. We use, in our book, they use theta rather than u for these. You could use u if you want to, but I'm going to do this substitution, x equals sine theta. Then, what is dx going to be? You just do the derivatives. Cosine theta, d theta, of course. You always put these in there. And we're going to plug stuff in here. So when I do my substitution, it becomes square root 1 minus, and you just stick this where x is. So it's 1 minus sine squared theta. And then dx becomes cosine theta d theta. All right? It does not look simpler than what we started with. But I'm here to tell you, it's gonna work out great. One thing we need to do is change the integration values. All right, and this is a little tricky, but what should we have if I say x equals 0? This means what is the corresponding value for theta? Well, it would say 0 equals sine theta, and then you just have to say what is the theta going to be? If I want sine theta to be 0, what does theta have to be? Yeah, actually there are a few answers. Somebody said pi because sine of pi is 0. Somebody else has said 0. I'm going to use theta equals 0. And then what about the other one? X equals 1. Okay, so this would mean that 1 equals sine theta. What's the theta you need to make the sine equal 1? Pi over 2, yeah. I hope you remember your values for sine and cosine. You know, the graph of sine is like this, where this is pi, this is 2 pi, this is pi over 2, right? Pi Day's coming up, by the way. Yeah, it's on Sunday. My kids have already requested that I make a pie. I'm doing it. I haven't decided what kind. Apple, yeah. Apples aren't really in season. I made a sweet potato pie for a couple months ago. It was really good. I've never. It's like a dinner pie? You think so? I don't know. I had it for dessert. I never had sweet potato pie, and I've always heard how great it is.
You should like surprise them and give them chicken pot pie or something totally off
We
that
ha-
they're not going to expect.
We often have, like, the math department has, faculty has a little pie day party where we have like a full meal, all pies. Yeah. I already got the Pi Day pie in Animal Crossing. Only available for the next week in the Nook shop. Yeah, one of my kids is an Animal Crossing fiend. Okay, so where I was, I'm still thinking about that sweet potato pie. The values here, the theta values, the x values were 0 and 1. These translate into theta values of 0 and pi over 2. All right. Now, when we look at this, ordinarily the purpose of a substitution is to make the integral simpler. This does not look all that simpler, but we can simplify, actually. Anybody have a suggestion how we can simplify this? That's right. 1 minus sine squared is cosine squared. So we have square root cosine squared theta, cosine theta, d theta. And what can I do with square root of cosine squared? It is just cosine. So this is now integral 0 to pi over 2, cosine theta. I got another cosine theta. Those come together and gives me a cosine squared theta. And how can I handle cosine squared theta? I want to integrate cosine squared. Yeah, how about those same formulas that we were just using in the other section? So this I'm going to do 1/2 1 plus cosine 2x. I got that right? I think so. Pi over 2, yep, thanks. I was concerned about getting the integral right. All right, and now we can do the integral, right? What do we get? I'm supposed to get pi over 4 at the end. I want to try and actually see if we really do get pi over 4 as the answer. Factor out the 1/2. Inside, I got 1 plus cosine 2x. I made it an x. It should be theta, right? The x's are gone. Never to return. And when I do the integral, do the antiderivatives, 1 becomes theta plus cosine 2 theta becomes 1/2 sine 2 theta. And I plug in 0 to pi over 2. Right? I think that's right. Okay, plug in pi over 2. I get, I'll do it down here, 1/2 pi over 2 plus 1/2 sine of 2 times pi over 2. That's sine of pi, right? And then minus, plug in 0, 1/2, 0 plus 1/2 sine of 2 times 0 is 0. And I believe all of that stuff is 0 except for the pi over 2 at the very beginning. This is 1/2 times pi over 2 plus 0. Sine of pi is 0, and then minus 1/2. This is 0. Sine of 0 is also 0. So you really do get pi over 4 as the answer. Kind of satisfying to me that this actually works. It is a bit of a journey to get there. And it all starts with this, in my opinion, very strange substitution at the very beginning. All right? You have to just kind of pull that sine theta out of nowhere, even though nothing about the integral really looks like a sine or a cosine should be helpful at all. But
I was just a little bit confused with that stuff, really the first step.
yeah,
If you're looking at it, because it's an integral, how do you know that it's equal to y? When you say like y equals 1 minus x squared, or like y squared equals 1 minus x squared, how do you know to set that equal to y?
oh, so from like all the way back here, when I thought of it this way.
Way back here.
Yeah, so when you, any integral that you do, like the definition of the integral, the definite integral is the area under the curve of,
Wouldn't that be equal to y prime?
not thinking of it as an antiderivative, but thinking of it just as the area under the curve of something. So like, for instance, this is the area, well, here's one. You can actually do this one.
So essentially, the integral represents separate things. It can represent antiderivative, it also represents area under the curve. They're not necessarily the same.
They are the same.
So then,
So
I'm still thinking of it as an antiderivative.
So if you want to do this integral as an antiderivative, you can do, this is using the fundamental theorem of calculus, 1/2 x squared, and I plug in 0 and 1. I get 1/2 from that, because when you plug in 1, it's 1/2 1 squared minus 1/2 0 squared, which is 1/2, all right? Or you can think of it as the area under the curve of this function, x. And that, as an area, would be this area right here, where this goes over to 1. And that also equals 1/2. But remember, this is the area under the curve of this function. It's not the area under the curve of the antiderivative. Maybe that's what you were thinking. It's the area under the curve of this function. The antiderivative is x squared, which is not, that's not the graph that I'm drawing down here. Right. Yeah. Yep. But this approach of thinking of it as the area of a particular picture, that approach is almost never helpful. It only works if that picture is already something you know how to find the area of, which typically it's not, you know. If it's a triangle or a circle or something, it'll work. But in any other example, it won't work. So as a general purpose method, you don't want to think of things in terms of areas. You want to try to do the antiderivatives or whatever. All right. Let's try one more. These take a few minutes to do, as you've seen. Let me just tell you the general strategy here. So what I just did, in general, there are two different trig substitutions we're going to talk about, and this is one of them. So in general, if we see something that looks like square root a squared minus x squared, where that a can be any constant. So in this case, it was just a 1. But this same trick will work even if it's a different constant. If we see this, you do the substitution x equals sine theta, dx equals cosine theta, d theta, and then rewrite using 1 minus sine squared theta equals cosine squared theta. That's what we just did in the example. Now, if it's not a 1, if you have that a instead, then the appropriate rewriting rule that you're going to use is this. A squared minus a squared sine theta is a squared cosine theta, cosine squared theta. That's the same. If you multiply through everything by a squared instead of 1s, what you get is this. A squared minus a squared sine squared theta equals a squared cosine squared theta. All right, this is a general principle which you should, I don't know, put this in a box or something. This is the basic strategy for doing this kind of trig substitution. If you see that square root kind of thing, this is how you should do it. So let's try another example which uses the same kind of trick. Let's try this one. I'm going to do as just a pure antiderivative, not with integration boundaries. So you will see we don't have to do the translating of the x values, which is nice, but a little hard step at the end. Not too hard, but an extra step at the end. Okay, anyway, now I'm a little concerned about this x squared in the denominator, but let's not even think about that for now. Let's just do the trig substitution. When I see this upstairs, 9 minus x squared, I'm going to fit it into this general principle here. Sorry, up here, can I fill in? I hope you left enough space to fill this in. I meant to put the a's in front of there. X equals a sine theta. Sorry about that. That extra constant there, this is the effect of that extra constant. The example we just did, it was 1, so you didn't see that. But in general, if it's a squared, you put a in the substitution. So here I see 9 minus x squared, 9 being 3 squared. The appropriate substitution to do is x equals 3 sine theta. And that means the dx equals 3 cosine theta d theta. And I'm going to plug all this stuff in. We don't have to worry about translating the boundary values because there are no boundary values. So plugging everything in, up top it says square root 9 minus, now x squared is going to become 9 sine squared theta, right? X had a 3 in it, so I had to square that 3, and it became a 9. And then the sine theta becomes a sine squared theta. It is, yeah, x squared. So when you square this, the 3 gets squared and becomes a 9. The sine theta gets squared and becomes a sine squared. Yep. And then I still have the denominator of x squared, which I'm going to also substitute 9 sine squared theta. And then dx, sorry, I forgot to write dx in my original integral. Dx becomes 3 cosine theta d theta. I have a tendency of leaving out the d whatever, unfortunately. All right. As before, it looks more complicated now than it was before, but actually this is not so bad. We have square root 9 minus 9 sine squared theta. Inside the square root, I'm going to write that is 9 cosine squared theta. All right. This is what I said before. This is the rewriting rule when you have that extra constant out front. It comes from the original rewriting rule, but just multiplied through everything by a squared. And then in my denominator, I still have 9 sine squared theta. And over here, I have 3 cosine theta d theta. All right. What can we do to simplify? What happens in the numerator there? Square root of 9 cosine squared theta. What's that going to be?
3 cosine.
3 cosine theta, yeah. The 9 gets the square root and makes it a 3. And the cosine squared theta gets the square root and becomes just cosine theta. On the bottom here, I have 9 sine squared theta, and then I have another 3 cosine squared cosine theta d theta. Okay, looks to me like all those constants are going to cancel, right? I have a 9 in the denominator, but a 3 times 3 in the numerator, and I end up with cosine squared over sine squared. Cosine squared theta over sine squared theta. Now this integral you could try to do by the methods that we talked about before, about product of sines and cosines where the powers are all even. Although in this case there's a little sort of shortcut. So sometimes at this point you do need to use those tricks from before, the previous section. In this case though, there's a little shortcut, and that is cosine over sine is cotangent, and there is a formula for the integral of cotan squared. I don't know if you remember this formula. I myself do not. Yes, I would give you this formula. It is minus cotan theta minus theta.
That's the integral of
That's the integral. Yeah, this is just a formula you would look up somewhere. So when you're doing the homework, you may boil these down after substituting and simplifying as much as you can. Hopefully you will end up with something that looks that either you can just do because it's easy to do, or you can look it up somewhere. All right. Now, we're almost done with this one, but not quite. Why not? Because I have thetas here. I would like to express my answer in terms of x, right? The original variable was x. So, and this is a little tricky in this kind of problem. I want to write the answer in terms of x. In an ordinary U substitution, this is always easy. You just plug the x's back in. What's the problem here? The problem here is we do not have the appropriate formula for x to be plugged in. Like, really what we need is a formula for theta in terms of x. But we didn't. We started off with x in terms of theta. A question or a substitution? Or, I mean, a suggestion? Yeah, right. You have to take this and solve it for theta in order to plug in for theta down here. So I begin with, I go back to x equals 3 sine theta, and we have to solve this for theta in terms of x, right? That will be plugged in. Yeah, we're going to have to do the inverse sine. So what I would do is first divide both sides by 3. It says sine theta equals x over 3. And this means theta is inverse sine x over 3. And this is what I am finally going to plug in for theta. So my final answer, almost, is minus cotan of inverse sine x over 3 minus inverse sine x over 3. This is in terms of x. All right? Yes. Now, one more step. So you could leave it at this, and this is fine as an answer, but The book likes to simplify this a little more, and I kind of like it too. So I might, on a test or something, I might say something like, simplify as much as you can any inverse trig functions. And this is something we've done before. When you see an inverse trig function inside of an ordinary trig function, this can be simplified. Remember, we did that for things like, what is sine of inverse tan of 3x or something like that. You can simplify that, all right? This is what I want to do. That was just a made-up example. What is this? Cotan of inverse sine x over 3. Remember, the way to do it is you draw a triangle whose sine is equal to x over 3. So I'm going to draw a triangle where the sine is x over 3. This is the angle I'm looking at. The sine of this is x over 3. And then I want to know what is the cotangent of that. So this is the triangle. We can determine what that side is based on the Pythagorean theorem. What's that side going to be? If I call it a, then it's x squared plus a squared equals 3 squared, right? That's the Pythagorean theorem. And so we can solve for a here. This is 9 minus x squared, I think. Square root of 9 minus x squared. Actually, this looks familiar. That's the thing that we were talking about at the beginning of the problem. That should not be a surprise. 9 minus, the square root of 9 minus x squared is already something that's relevant in this problem, so it's not a surprise to see that appearing again. Anyway, what is the cotangent of this? So the cotangent, it is the adjacent over the opposite, right? Cotan is 1 over tan. Tan is opposite over adjacent, so cotangent is the reciprocal of that. And that would be this. Adjacent would be that square root thing, divided by the opposite, which is x. So that is, that cotangent part in my answer is actually equal to this. And so my real true final answer is minus, and then the cotangent is this thing, 9 minus x squared over x, minus inverse sine x over 3 plus c. Yeah, that really you can't simplify inverse sine of x over 3. Inverse sine of x over 3 really, it represents this angle. This is the angle whose sine is x over 3, but there's no way to re-express that. All right, and I think that's our time for today. These trig substitutions are difficult in my opinion. No, the quiz on Friday covers only what's on the homework due tomorrow, which does not include this. All right, see you all later.